What's the difference between a ballerina and a black hole? Of course, a ballerina does not represent the death of a star. The event horizon of a ballerina is really small. You wouldn't be able to see it. It lies somewhere inside the ballerina. Light can easily escape the ballerina. The ballerina is not home to the strangest phenomena in the universe. It seems they are quite different, huh? Well, apparently, according to physics, they have at least one thing in common. When the ballerina starts spinning, she experiences the same physical process as the black hole. It's a pretty simple concept of physics, basically ubiquitous in the universe: the conservation of angular momentum. This conservation law helps us explain why the ballerina spins faster if her arms are close to her body. But it also explains why it is so hard to get sucked into a black hole. Keep watching the video to get to know more about black holes and ballerinas. Why is it so hard to fall into a black hole? I'm sorry, my friend, but the truth is, falling into a black hole is no picnic. It is actually way harder than you think. Science fiction movies and books always told us black holes are huge sources of gravity, so strong that nothing can escape them, not even light. They are thought to be the ultimate absorbers, the infamous singularities, rifts in the fabric of space-time where laws of physics break down. Yet it is way easier to fall into a star than into a black hole. Do you think I'm talking nonsense? Well, listen to this. If you had a galaxy filled with black holes and one filled with stars, which one do you think would be the easiest to cross with your spaceship? I'm telling you, it's the one with the black holes, because even if they are the ultimate absorbers, their huge sucking effect is limited to a really small radius. As long as you stay away from it, you won't fall, because black holes are like pins in the space. And although they are able to distort it, the curvature is only really peaked around the singularity. Anywhere else, you're safe if you keep a certain distance. For stars, the thing is much more complicated. The gravitational curvature produced by a star, it being a sphere, is much more spread in terms of space. If you happen to cross a galaxy filled with stars, you should be very careful not to enter their gravitational field. And this would be harder to do because you will have less free space to travel. I think you get what I mean. But there's so much more than this. These weird galactic holes are so hard to get inside. Einstein himself believed you couldn't get inside them at all. We don't actually know if he was right or wrong, but we do know physics does the best it can to avoid you falling into a black hole. Sometimes we have also seen material being ejected from black holes, but we'll come to this later. I think everybody here is familiar with the idea of a black hole. These objects have so much mass in a so small area, and therefore they're incredibly dense. The space curvature becomes infinite. You can't escape from a black hole. Bolt can't escape from the black hole. Maybe Elon Musk could come up with some clever ideas, but the thing is, from what we know so far, not even light can. Once you cross the event horizon of a black hole, you can say goodbye to the rest of the universe. However, this doesn't necessarily mean you're going to fall into it. Before that happens, you might probably start orbiting around the singularity for billions of years. Of course, the closer you get to the black hole, the faster you spin. But this doesn't make you fall into it. Just like a slide gets steeper and steeper the further along you go, so the black hole speeds you up to relativistic speeds the closer you get to the center. But almost in all circumstances, you will not find yourself approaching the singularity, and this is where the conservation of the momentum kicks in. But to really understand this concept, we have to talk about the structure of a black hole. It usually has an accretion disk surrounding the singularity. Scientists know that because they have observed it. An accretion disk is a flattened, circular, or elliptical structure that is formed when material falls towards a strong gravitational force, such as a star or a black hole. Accretion disks are found surrounding a variety of celestial bodies, from relatively small regions of a few thousand kilometers around white dwarfs and neutron stars, to protoplanetary disks around very young stars. The biggest accretion disks, on the scale of the fact that accretion disks exist over a huge range of scales and in apparently very different types of systems, suggests some common physics behind their formation. Because angular momentum is always conserved, small rotations in any infalling material are amplified as it collapses inwards towards the star or black hole. This is something like the motion of spinning ice skaters or ballerinas who speed up as they bring their arms inward. Allow me to explain it better. Let's say you have a group of objects. According to physics, the motion of those objects, also called momentum, must always remain the same. This is what we mean when we say the momentum must be conserved. Basically, if a particle with momentum bumps into another particle that is standing still and both bounce away from each other, the amount of total momentum for the two particles must be equal to the initial momentum of the first particle. This is the same principle that holds for astronauts on the International Space Station when they move to keep themselves afloat, or what happens when the ignition starts, the engines are fired, and the rocket lifts off. Once you add up the momentum imparted to the air by the propellant going down and the amount of momentum given by the rocket going up, then the upwards and downward momentum are equal, resulting in a net zero momentum, which, by the way, was the same you had when the rocket was standing still on the launch platform with no engines on. But what has this got to do with black holes and accretion disks? Accretion disks are not actually a necessary part of black holes. According to physics, simple black holes exist. They are just found there alone and sad. They're not complicated, and they just have a mass, a spin, and an electric charge. However, some black holes are more interesting than others. For instance, if a star is found near a black hole, it can start being torn apart by the black hole's gravitational pull. Over the time scale of millions of years, material from the star starts spiraling around the black hole, getting sucked and forming an accretion disk. This accretion disk can take something like 100 to 1 billion years to be completely absorbed by the black hole. Before that happens, the matter coalesces into a flat ring around the black hole's event horizon. And it does not fall in, due to the conservation of the momentum. In this case, we talk about angular momentum, since the disk is rotating. We will use the example of a ballerina. The ballerina has her arms outstretched and is spinning on a single point. What will happen if the ballerina suddenly tucked her arms close to her body? Intuitively, she will start spinning much faster. This is because the hands of the ballerina carry angular momentum. When the arms are outstretched, the momentum in the hands is traveling at a certain speed. And when the ballerina tucks her arms, the momentum is still trying to preserve that speed. But now the hands are traveling along a much shorter path. Since it is doing so at the same speed, the ballerina rotates faster. This is a classical book example of the conservation of angular momentum. The beauty of physics is that results are quite general, and they can be applied to the small scale as well as to the big cosmic scale. The material surrounding a black hole is orbiting in the accretion disk, caught in the black hole's gravity. The conservation of angular momentum is always taking place, so as soon as the material gets closer to the center, it gets sped up, moving at the same speed on an ever smaller orbit, just like in the ballerina example. This is what happens when material spirals towards the center of a black hole. So you have to imagine this material stolen from another star, getting sucked and spiraling into the black hole as it speeds up to the relativistic speeds. The accretion disk material eventually reaches a point where it cannot go any faster. It's hit a roadblock due to the limit imposed by the speed of light. At this level, collisions and friction heat up the matter around the event horizon. Everything becomes really hot. I don't suggest you be there. You would die in an oven. The temperature can reach temperatures up to 10 million Kelvin. When this happens, atoms collide, and these collisions cause them to give off more and more of the atom's mass, transforming that into energy, according to Einstein's famous law, E equals mc squared. Scientists think between 10 to 40% of an atom's mass is given off this way in the form of energy. Due to this energy emission, the accretion disk is observed to be really, really bright. But how bright can it get? The brightest such disks are known as quasars, and they can reach brightnesses that exceed 1,000 times the total brightness of every star in the Milky Way galaxy combined. But what is even more interesting is that a small fraction of supermassive black holes, the ginormous ones that lurk at the centers of galaxies, also called quasars, fire off light-speed jets of particles as they snag. Astronomers don't know what powers jets, but they think they're powered by the coupling of a black hole with the accretion disk. The most popular explanation of how jets form is that the fast-spinning accretion disk, which contains charged particles, will produce a powerful magnetic field that is in contact with the black hole. If the black hole is spinning, it drags on the field, winding it into a tight cone at the rotational poles of the black hole. It is this twisted field that accelerates particles away from the black hole as jets, and in the process extracts energy from the rotation of the black hole. So to sum everything up, it's possible, not easy though, to fall into a black hole. But that's not the only way to go. It is also possible not to fall into them too. There are a lot of ways a black hole could destroy you. You would most likely die from the generated heat while spiraling in the accretion disk. You could get spaghettified if you made it to the singularity. Or maybe you could become part of a plasma jet injected into space at relativistic speeds. I would recommend you not to get close to a black hole in any case.